So we're going to start chapter 3 now, and in chapter 3 we're talking about the different ways that we can visually represent data. So we're going to look at some different types of graphs and graphical representations. But before we do, there's another element of the analysis of data that we need to consider in a little bit more detail, and that's the idea of an outlier. Now, you've probably met the concept of an outlier rather informally before. An outlier is an extreme value in the data set, but one that lies outside of the standard or ordinary pattern of the data set. So it's one that seems so very different that it makes you suspicious. It makes you wonder whether it really should or shouldn't be there. Sometimes they're valid, sometimes they're not valid. Up till now, whenever you've been thinking about the idea of outliers, you've probably just looked at data values and gone, that one seems like it's a bit too far away, that's an outlier. But what we're going to do now is look at it a bit more mathematically and come up with some formulas to help us identify mathematically whether or not something is classed as an outlier. So, we've got two ways so far that we've looked at analysing data. First of all, we've considered the median and the quartiles, and with that, of course, the interquartile range as our measure of spread. If we are looking at median and quartiles of data, then the way we consider outliers is this. At the top end, something would be an outlier if it's a certain multiple of the interquartile range above the upper quartile. So what I mean by that is you go to the upper quartile and then you might add on 1.5 times the interquartile range, or 2 times the interquartile range, or maybe just one lot of the interquartile range. And if you have any values that lie above the value of this calculation, then they're classed as outliers. You do the same thing at the lower end. You go to the lower quartile and you subtract this multiple of the interquartile range. So you go back down from it. And then if you have any values that are below that, they're classed as bottom end outliers. Now, it might be, however, that you're analysing your data using the mean and the standard deviation as your measure of spread, because we learned that these two go together. In that case, in order to identify outliers, what you do is you start from the mean and you add on a certain multiple of the standard deviation. So you might go to the mean and add on, say, 2 standard deviations or 3 standard deviations. And if you have any values that are above that, they would be classed as outliers. But similarly, if you go to your mean and you take away or subtract a certain number of standard deviations and have any values below that at the lower end, they would be outliers too. So you can have upper end outliers and you can have lower end outliers. So let's have a look at example 1. I haven't copied out the numbers here because there's 30 of them, but if you have a look in example 1, you'll see a list of numbers that represent the blood glucose of 30 females, and the units here are micromoles per litre. Now, you're told that for these data, because it can vary for different sets of data, for these data an outlier is an observation that's 1.5 times the interquartile range above the upper quartile or below the lower quartile. So for the data that we're given, we're going to first of all find the quartiles. Now, for our lower quartile then, remember we start by finding the position that it's in. So we're going to go, there are 30 data values, we divide it by 4, so that gives us 7.5. Remember from one of our previous videos, if that's a decimal, we round up, so we're going to pick the 8th value in the list, and the 8th value is 3.2. So that's our lower quartile. Now our upper quartile is going to be 3/4 of the way along the data. So that's going to be, we go 22.5, round it up to 23, so the 23rd value in the list. So let's look along the list of numbers, and that's going to be 4.0. We're also going to find out the median, because the question asks us to find all the quartiles, not just the upper and the lower quartile. Remember, the median is one of the quartiles too. So 30 over 2 is 15. Now remember, if this comes out as a whole number, you go halfway between that and the one above. So we want the 15.5 value. So the halfway between the 15th and the 16th, they're both 3.8s. So that's going to be 3.8 there. Now, we're asked to work out if there are any outliers in the data. So the first thing we're going to do is work out the interquartile range. So our interquartile range, which is Q3 minus Q1, that's going to be 4 minus 3.2, so 0.8. Now the outlier calculation uses 1.5 times the interquartile range. So let's write down that. 1.5 times by 0.8. So we have got 1.2 there. So what we're going to do is, if anything is 1.2 above the upper quartile, it's an outlier. Or if it's 1.2 below the lower quartile, it's an outlier. So Q1 minus 1.5 times the interquartile range would be 3.2 minus 1.2. So that's going to be 2. Now, are there any values that are less than 2? Yes, if we look at our list, there's one of them. It's 1.7. So 1.7 is an outlier. So let's look at here then. The upper quartile plus 1.5 times the interquartile range. Our upper quartile was 4.0. So 4.0 plus 1.2 is going to be 5.2. Are there any upper outliers? Well, the highest value is 5.1, so it's not above this. So there are no upper outliers. So only 1.7, that's our only outlier there. Now let's have a look at example 2. In example 2, we are given a list of numbers, 12 of them, and they are the length in centimetres of giant African land snails. Now, we've been given some summary statistics here. So although we have the list of numbers in the question, we are told that all the numbers add up to 252, and the squares, the sum of the squares of the numbers is 5,468. That means when we're asked to find the mean and the standard deviation in part A, we haven't got to do a lot of work with the numbers. We're given the hard work already. So for the mean, we know we do the sum of x divided by how many numbers? Well, that was 12. Let's make a note of it here. We were told that in the question. So we've got 252 divided by 12, which is 21. So this was centimetres. Then standard deviation, we know that that's the sum of x squared over n minus the mean squared and then square root of all of that. So we've got 5,468 over 12 minus 21 squared and square root all of that. So our standard deviation is 3.83 centimetres to 3 significant figures. Let's stop and make sure we know what the numbers represent. So we've got 12 giant African land snails. The mean length of these snails is 21. The standard deviation is 3.83. So on average, these snails vary from 21 by 3.83 centimetres. Now, we're told in part B that an outlier is going to be, for this question, an observation that is 2 standard deviations above or below the mean. And we've got to identify if these data actually have any outliers. So let's have a look. Our mean was 21. If we add 2 standard deviations, where do we get to? 21 plus 2 lots of the standard deviation, and we get to 28.66. Or, at the lower end, if we go from the mean and subtract 2 standard deviations, we've got 21 minus 2 lots of 3.83, and that gives us 13.34. So if there are any snails that are less than 13.34 centimetres, they'll be an outlier. If there are any that are above 28.66, then they'll be outliers. Now the shortest of all these snails was 17 centimetres, so there were no lower end outliers. The longest of them was 32 centimetres, so that means that we do have an upper outlier. 32 centimetres, just that one snail there is an outlier. Now, I need to talk to you just for a tiny little bit about what we do when we find outliers, because in this case it's quite possible that there could be an African land snail of 32 centimetres. Yes, it's unusual, as the data shows us, it's an outlier, but it's still possible. So sometimes outliers are still a genuine part of the data, they're just a surprising one or an unexpected one. However, sometimes there might be outliers because they're errors. Maybe somebody had written something down wrong, it's a recording error, or maybe there was some kind of equipment error in the gathering of the data. In that case, the outliers you get have a special name and they're called anomalies. That means something's gone wrong here. This shouldn't be in our data. A 32 centimetre snail wasn't an anomaly, it was just an unusually humongous snail. However, let's look at these data here. These are the ages of people at a birthday party. And looking along, I can see we've got one person at this party who's 165. That's clearly an anomaly. That is not meant to be there. Let's do this mathematically. I mean, it's kind of obvious, isn't it? But let's do it mathematically. Let's say the outliers are anything that's 1.5 standard deviation above the mean. So for these data, the mean is 47, the standard deviation is 44.02. So if I go from the mean and I add 1.5 times my standard deviation, what do I get? 47 plus 1.5 times my standard deviation. That's an age of 113.03. It's almost plausible. You could potentially get an 113-year-old, although it's highly rare. 113.03. So what we're saying here is if there is any age recorded that's above this, it's an outlier. Well, we have this 165-year-old. That clearly is an error in recording in the data. So this is an anomaly. In the case of an anomaly, what we do is we remove that data value because we're confident it shouldn't be there. And this is a process called cleaning the data. And that's getting rid of anomalies, getting rid of things that are there as a result of some kind of error and that shouldn't be there. And we clean the data before we do any kind of analysis. So could you have a go at exercise 3A, please?